The rule of 72 is a rule of thumb in financial math that has to do with the doubling time of an investment that gets compound interest. So if your money is growing at a certain interest rate and it's getting compound interest, you might wonder, how long will it take until the money has doubled? In this video, we're going to go over the rule and we'll talk about the mathematical reason why the rule works. Now, the rule is sometimes called the rule of 70, sometimes called the rule of 72. We'll actually use 70 to start out, mainly because it's more accurate, but later I'll mention why both numbers are sometimes used. Now, the rule says if an amount of money grows at an annual interest rate of R% compounded continuously, it'll take roughly 70 divided by R years to double. So for example, if your money is getting 2% interest, it'll take about 35 years for the money to double. Or if you're getting 10% interest, your money will be doubling every 7 years. So what is the math behind this rule? That's what we're going to talk about in this video. Now, I'll give you the punchline right now. It turns out that the reason the rule works ultimately boils down to the fact that natural log of 2 is about 0.70. So in this video, we'll explain the math behind the rule. We'll talk about why is 72 sometimes used, and we'll talk about what if we don't have continuously compounded interest? What if our interest is compounding monthly or daily? Can we still use the rule of 70 in such a case? And it turns out that you can. Now, finally, at the end of the video, I'll also mention how we can use the rule of 70 in practical terms to actually make money. Now, one thing I'm assuming is that you're familiar with the idea of compound interest. And we have these compound interest formulas. If you're not familiar with them, then I have some videos I'll put in the description where I explain them. Now we're going to begin with the continuously compounded interest formula because the math just works out a little bit more simply in that case. But before we go into the algebra of why the rule works, let's look at a graph on Desmos. Okay, so we're here in Desmos and I've graphed A equals P times e to the RT, and I've made sliders for P, the initial amount of money, and R, the interest rate. And you'll notice here that the curve is in red, and this curve represents how much money is in the account at any given time T. Now, I've set the slider for the initial amount of money to be $10,000 and for the interest rate to be 5%, so R equals 0.05. And notice this point 0, 10,000 represents that at time 0, the initial time, there's $10,000 in the account. This point over here is going to tell us about the doubling time. So I've made a little green horizontal line that represents the initial amount of money, and I put another green line here that represents double that amount. So this would be $20,000. Well, this point tells us that at time t equals 13.86, or after 13.86, that the money has doubled from 10,000 to 20,000. Now, 13.86, if we round it to the nearest year, would be 14 years. Now, notice that if we go to our slider and change P, the initial amount of money, the doubling time does not change. So if you start out with $15,000 and you double to $30,000, the doubling time is still about 14 when we're using 5% interest. So that initial amount of money doesn't affect the doubling time. Now, the interest rate does. So at 5% interest, notice that we doubled after 14 years. If I moved it to, say, 7%, it would double after about 10 years. Or if I moved it to 10%, we'd be doubling after about 7 years. Or if we moved it to 2%, it would take about 35 years. Now, we'd have to zoom out here a little bit. Now, based on that graph in Desmos, we can make a little table. So notice in the table I have the interest rate in the left column and the doubling time in years in the right column. And we're going to approximate to the nearest year. But remember, at 2% interest, it took about 35 years for the money to double. With 5% interest, it took about 14 years to double. 7% took about 10 years. 10% it took about 7 years. And I didn't do it, but at 14% it would take about 5 years to double. Now, from this table, we can notice a couple things. First of all, as the interest rate goes up, the doubling time goes down. And that's pretty obvious because the higher the interest rate you get on your money, the faster it will grow, so the less time it will take to double. But second, you might observe that if we multiply across the table, we always get 70, or about 70 since we're rounding to the nearest year. So 2 times 35 is 70, 5 times 14 is 70, and so on. So just looking at this table, we could discover the rule of 70. But why does the rule work from an algebraic standpoint? So let's explain based on an example. If $10,000 is invested in an account that gets 5% interest compounded continuously, how long will it take for the money to double? So what we need to do is to solve this equation. So on the right-hand side, we've used the continuously compounded interest formula, the PERT formula, where we've just plugged in 10,000 for P and 0.05 for R. And this tells us how much money is in the account after T years. But we want the money to double, so we set this equal to 20,000. Now, the value of T that solves this equation will be the doubling time. So how can we solve for T? Well, the first thing we'll need to do is divide both sides by 10,000. And if we do that, then on the left-hand side, we're just going to get 2. And on the right side, the 10,000s divide out, and we just get e to the 0.05t. Now, to get rid of the exponent, we'll take the natural log of both sides. And on the left side, we have natural log of 2. And on the right-hand side, we have natural log of e to the 0.05t, which simplifies to just 0.05t. And finally, to solve for t, we divide both sides by 0.05, and we get that t equals natural log of 2 divided by 0.05, which is about 13.86. This means it takes 13.86 years for the money to double. And notice that's about what the rule of 70 would say. The rule of 70 says if you're getting 5% interest, it should take about 70 divided by 5, which is 14, years to double. Now, a couple things we want to observe is that, first of all, the initial amount of money doesn't matter for the doubling time. So if we go back up and look at our equation, if our initial amount of money had been something different, so instead of $10,000, if we'd had, say, $15,000, our doubled amount would be $30,000, but when we divide both sides by 15,000, we would still end up with 2 right here. So no matter what your initial amount of money, you always end up with 2 on the left side. So that's the algebraic reason why the initial amount of money doesn't affect the doubling time. Okay, so the second thing I want to observe is that the natural log of 2, if we plug it into a calculator, is about 0.69314, or about 0.70. And this is going to be the key to the rule of 70. So notice 100 times natural log of 2 is 69.314, which is approximately 70. So how does this give us the rule of 70? Well, notice that we found our solution to the problem that we just did to be natural log of 2 divided by 0.05. But we can rewrite this by, first of all, multiplying the numerator and the denominator by 100. And we get 69.314 divided by 5, which is about the same as 70 divided by 5, which is 14, or 14 years. And isn't this what the rule of 70 would say for the doubling time? 70 divided by 5 years. Now, what if we had a different interest rate other than 5%, such as 7%? How would things be different? Well, we would end up with a 0.07 here instead of a 0.05, and we would get this is approximately 70 divided by 7, which is 10, or 10 years. And isn't that what the rule of 70 would say? If you get 7% in interest, it will take 10 years to double. So notice that it's always 70 divided by your interest rate. So that's the algebraic reason why the rule of 70 works. Now, why is the number 72 sometimes used? In fact, if 100 times natural log of 2 is about 69.314, why would we ever use 72 instead of 70, since 70 is closer to 69.314? Well, the number 72 has more divisors than 70. So if we're trying to do quick calculations in our head, which is the whole point of using the rule, then 72 works for more numbers. So for example, if we get 3% interest, well, 3 doesn't go into 70 evenly, but it does go into 72. It goes in 24 times. So it would take about 24 years for your money to double if you're getting 3% interest. So that's why 72 is sometimes used. Now, what if the interest is not compounded continuously? What if it's compounded monthly or daily or some other way? Can we still use the rule of 70? Well, it turns out that we can. Now, with the rule of 70, it could really be called the rule of 69 or the rule of 69.314 because that's what 100 times natural log of 2 is. But when we use other kinds of compound interest, we don't always get 69.314. In fact, the exact number we should use will depend on the number of times you compound per year and also on the interest rate. But in most cases, the number of 70 works pretty well. So in this table, I've listed the exact number you'd need to use for various interest rates and for various number of times compounded per year. So up here we have interest rates 1%, 2%, all the way up to 50%, 100%. And over here we have the number of times you compound per year, so once a year, twice a year, compounding monthly or compounding daily. And notice that for continuously compounded interest, the number is 69.3 or 69.314, no matter what the interest rate is. And compounding daily is pretty close to compounding continuously, so you get numbers that are very close to that 69.314. In fact, most of the numbers in the whole table are pretty close to 70. The only numbers that are a bit off are when we're compounding only like once a year or twice a year, and when the interest rate is very high, like 50% or 100%. So the number 70 is certainly good enough to use in most cases. Now, what we've explained so far is the mathematics of the rule of 70, but I want to talk to you briefly about how you could use the rule of 70, the power of compound interest, to grow your money, and how to think about this from a mathematical standpoint. Now, someone once said that the power of compound interest is the eighth wonder of the world, and it's amazing how many people have become wealthy by it. Now, the S&P 500 is an index fund that tracks 500 of the largest publicly traded companies in the United States. And over the last 100 years, the average annual rate of return is about 10.5%, so a little more than 10%. So notice, according to the rule of 70, it's doubling in value about every 7 years. Now, inflation is eating some of that, right? Inflation has averaged about 3% per year, so inflation adjusted rate of return on the S&P 500 is about 7% per year. Again, that's the past performance of the fund, which is no guarantee of future performance. In some years, it's way up, maybe much more than that 10.5%. It might be 20 or 30%. Some years it might be flat. Some years it will go down. But that's the average annual rate of return. So inflation adjusted, it's about 7%, which means that it will double about every 10 years in inflation adjusted terms. Okay, so what does that mean for you? Well, if you can find some type of investment like the S&P 500 where you're getting a real rate of return of about 7% per year, then that the money that you put in will double about every 10 years. So if you start at age 20, I have a lot of young people watching my videos, a lot of college age students. So if you start investing at age 20, then by the time you're 70, that'll be 50 years. So the money will have doubled about 5 times. And 2 to the 5th power is 32. So you'll have about 32 times as much money in real inflation adjusted terms than when you put it in. So for example, if you put in $3,000 at age 20, and that might sound like a lot of money to you, and maybe it is a lot of money, or maybe not. I don't know what your financial situation is, but if you can put in $3,000 at age 20, then when you're age 70, you take that money out, it'll have grown to be about $96,000 or $100,000. Again, I'm just using rough numbers, kind of ballpark figures here. But then at age 21, suppose you put in 3,000 more. Well, then at age 71, you can take that money out and it'll be about worth $100,000. And then same thing at age 22, you put in 3,000, it'll be worth about 100,000. Now, again, this is just a rule of thumb and there's no guarantees here, but I think people who are smart with their money, people who are wise in their investments, they think about their future. Now, you may have philosophical reasons why I don't want to invest in the S&P 500 or these evil companies, but whatever your reasons are, I hope you will invest in your future. And by the way, if you've enjoyed this video, if you've liked this video, please put a like on it. Please put a comment at the bottom. It really helps my channel to grow and the YouTube algorithm really likes it. If you have any advice or comments about either the math or practically what to do with your money, put that in the comments. So thank you for watching and have a wonderful day.